All right. So today, we'll talk about, let's start chapter 12. Where it starts talking, we're going to say a couple more things about chapter 11, which is more just the introduction to rings. And we're going to focus a bit on factoring rings and what that looks like. So let me just remind you last time ended with a proposition, and as the proposition 11.8.4, and well, one part of it was if F is a field, then principal ideals and the math starts. The math means of F of X principal ideals X, where this function, polynomial F of X, is irreducible. That's what we're latching on to for this week. Really, we're going to be thinking about what is irreducibility, what is in the context of arithmetic, and then what is in the context of general rings. And something, I mean, when you're studying things like rings, because we have so many examples of rings of functions, we have arithmetic rings, polynomials. Interesting rings. We have all kinds of examples of these. The interesting thing in studying these is when you start seeing things go wrong. Things that you see that you would expect to happen because they happen in a million cases start not happening. And then you ask the question, okay, what is the subtle differences in these situations? So irreducibility, factorization, that's where we get some subtlety at the beginning of studying rings. That's it. So chapter 12. Start us off with kind of a section of one which deals with the integers. And just recall some of the things we know. What the theorem over. Take a look at it. These are the things that I would say we expect, we're familiar with, we would generally expect to happen in a very nice setting. We had a nice ring. One is so A is this first notion that all the ideals of the integers are all principal. We've already talked about this notion of a principal ideal, namely, but we'll get into it a little more this chapter, where every ideal of the ring is a principal ideal. We also have this theorem early on that if we have two integers, this is when we just study dealing groups, subgroups of integers, that we could take the sum of two subgroups, Z A and Z B, which now we can recognize as ideals as well. And we'll get some, because it's principal, we'll get Z times some element G. And we have a host of properties of Z. And these two properties will be summarized today to mean that D is, make the definition that D is the greatest common divisor of A and B. So there's a notion here that just comes from, which defines this term greatest common divisor in general rings, not just And then we have this theorem, which we've used in a few different contexts. Used it just last week when we talked about product rings and finding. This is an interesting thing. C is very interesting. I didn't get a chance to really talk about it as much, but it's a property, right, in integers. When you're in elementary school, you learn what a prime number is. You don't learn that this is the defining property of a prime number. Okay, if P equals A times B, then A or B is 1. You don't have this kind of property. P divides a product of integers, then it divides one or the other. That's not something that is used as a definition of a prime. Maybe equality, it may be something that is equivalent to a prime. It's not a definition. And this we're going to abstract into the notion of prime ideal. It's a notion of a prime element of a ring. And then finally, we have this guy. I tested you all on early in this class. Just see, survey, let's say survey. Everybody on whether or not people knew the fundamental theorem of arithmetic. And of course, you all knew, but you just didn't know, like it was called the fundamental theorem. It's a fundamental. Why even give it a name? Again, not to over repeat myself, but the interesting thing to me about studying rings is when you start seeing things break down. And this theorem does break down in some cases. Almost all cases of interest. And, well, maybe not all cases, but I say the majority of cases will break down, and then it's kind of very interesting how it breaks down. So what we would like to see is sort of what are the nice cases of rings where we can have this fundamental theorem of arithmetic? How do we express this fundamental theorem of arithmetic in general ring? And what what are examples when it fails? I'm not sure how much we're going to say. We'll say a little bit about what happens when it fails. Rings. We have some vocabulary. In order to do this, make this project work, which is this generalization of these kinds of ideas to more general rings. And I did realize in the problem section last week that for Artin, all rings are commutative, which is fine. As long as we're just going to say dealing with commutative rings. A ring in general is not required to be commutative. But we can certainly limit the discussion to commutative rings. So if we're dealing with a commutative ring, we may want to know how to abstract a lot of these notions to a general commutative ring. Replace integers by ring R. So we're going to need some vocabulary for that. R being a commutative ring. Make a table, vocab table. Yep. We'll have two different kinds of definitions. One will be sort of wordy, and the other will be math. First notion is a unit, and we've already defined a unit. Everything is in R. Okay, U has a multiplicative inverse. Now, let's look back at 1. The vocabulary of ideal, as I said earlier in the lectures, was an ideal was an idealized number. That was the early notion, that we could replace numbers with ideals and they behaved like wonderfully, or they behaved in some natural, more natural way. And so this first thing that every ideal is principal, A, we want to start saying taking principal ideals in particular very seriously. So let's see if we can't, in this mathy definition, describe a lot of these concepts in terms of principal ideals. So here we could take the principal ideal of U, and what would it be? Someone can tell me. U as a multiplicative inverse. What's the principal ideal? What is a principal ideal? Okay, so that's the generator of a principal ideal. Okay. So what is an ideal? An ideal is a subset of our ring. Okay, it's a subset of our ring satisfying some properties. It's an abelian subgroup in the additive operation. So it has to be a subgroup in that sense. And satisfy this other property that if I multiply any element of the ideal by another element of the ring, that's still in the ideal. So sort of closed under multiplication by elements of the ring. Okay, that's it. That's the notion of an ideal. Now, a principal ideal is just you take that one element Tim's talking about, right, and you look at all of its multiples. When you say multiple, you're multiplying by elements in the ring. All possible multiples of that given element. That's the principal ideal generated by that. So here we have an element U. It has a multiplicative inverse, meaning what does it mean that I have a multiplicative inverse? Yeah. I can multiply it to get the identity, right? So I can multiply U by some element V, and I get V times U equals identity. So that means that V times U equaling 1, this is an element of my principal ideal. All multiples of U are in my principal ideal. So 1 is in my principal ideal. But now 1's in the ideal. All multiples of any element in the ideal have to be in the ideal. What are all the multiples of 1? The whole thing. That's R. Okay. So to say U as a unit, okay, we can say U as a multiplicative inverse. That has a lot of words in it, or words. Or we can say the principal, we can write principal ideal of U equals R. So okay, they're whatever, you know. You should know both. You should be able to handle both. Okay. A divides B. Okay, what does that mean from the wording perspective? That means that B equals A times some other element in my ring. Some human. Now I have two elements, A and B. I can consider their principal ideals. And if B is a multiple of A, then B lives in that principal ideal. B lives in the principal ideal of A, generated by A. But if B lives in the principal ideal generated by A, then all the multiples of B also do. That says that I have one is contained in the other. So sometimes there's a little notation here. I don't see Art using this notation, but I might use it. I think I've told you before. That's the notation for A divides B. Very common. Not all of these have notation. All right. A properly divides. Properly divides. Okay, it's the same as this. But now we need that Q is not a unit. What this will mean is that have this, but there's not an equality here. This is not equality. You can say 1 or R. An equality would have a unit, and I think I may need here for this to be kind of correct. I may need one other thing here. So I might want, for all of these conditions, I'm going to want integral domain, which is, again, this means no zero divisors. Which is pretty okay. It's an assumption one often makes. There are versions of this without that condition, but I think it's better. Okay, so now here's another notion. This one comes directly from elementary school. I have a friend who's one of those gifted and talented teachers at elementary schools around here. Brings me questions from her gifted students. This one answers a question from one of her 9-year-olds, I guess. Well, okay, so the notion is A and B are associates. Yeah. And what it means is that A is equal to U times B for some unit. And the mathy version is that A as principal ideal is equal. And the question from the 7 or 8-year-old was, is -2 prime? -7. Like, what does it mean for a negative number to be prime? And the point is that when we start talking about more general rings, we want to be able to talk about the primeness of all the elements, whether something is or is not a prime element. Well, we can say something is prime if it's an associate of a prime that we. So from the integers, we can say yes, they're prime. And really, we can only talk about primeness up to being an associate. So -2 and 2, they generate the same principal ideal. So the definition of primeness is a question about the principal ideals. And therefore, we're not going to be distinguished positive or negative. I did not respond that way to the 7 or 8-year-old. But I said, yes, sure. We consider it.
Are -1 and 1 the only units in Z?
In the integers, yes. But another example that we'll look at today would be the Gaussian integers. So look at the integer ring. And so these are all elements that look like A plus B times I, where A and B are integers. And here, of course, you have more units, right? You have I and negative I in addition to plus or minus 1. So you can, and if you wanted, you can look at the Eisenstein integers. Those have 6 different. And then there's questions of factorization. So you want some notions that you can use in these more general cases. There are a lot of interesting. There are a lot of open questions. Irreducibility. So this is something that came up in the first proposition I put in today. So A is irreducible. That means that if we have A equals BC, then either B or C is a unit, or you could say A is an associate of B or C. I should say, an A is not a unit. A is not a unit. And so it's saying that basically anything that divides it is an associate. This is what you would say for primeness of a number. Saying this is how we define an element. A number is prime if only if it's divisible by itself and one. So if something else divides it, it must be. So the way of saying this is that A is not equal to R taken A. And this is, well, you can read this in another way, I think. Maybe someone can tell me what is another way of reading this condition. Well, another way of reading this condition is this is a maximal principal item. It's amongst principal items. This is maximal. It can be strictly contained in another. Second one. And then finally, we're going to do, we are going to define the notion of a prime. So P is prime. This means, again, I mean, P is not a unit. And if he divides AB. Yeah, I don't want to write this way. I'm going to use language here. This is the wordy way. Okay, good. If he divides AB, then he divides A over B. At least one. Or is taken to mean one or both. This can be written, AB is an element of principal ideal, implies A is an element of P, or you could write this as an equation with ideals, but I'm not. Okay, so this table really is, I mean, okay, we have 1, 2, 3, 4, 5, 6 definitions. And it's geared to really, as I said, to generalize a lot of these notions and to put in context of general rings these theorems and ask, do they hold? When do they hold? When do they break down? But they're important in that we need this kind of language. Right. So when do we get 12.1? 12.1. Now that we have the vocabulary, we can ask, when do we get everything? And what? By which I mean all of this theorem in its general ring. Well, you might think, okay, well, we've had this notion of a PID. And so maybe it works for all PIDs. Okay. Maybe. What we can do, though, definitely, is it does seem to work for two examples that we have at our fingertips, right? It does seem to work for integers and for polynomials with coefficients. But we had this division algorithm in both cases. We can divide and get remainders. And that allowed us to actually state almost identical theorems for those two cases. Indeed, we can abstract that idea of the division algorithm. But what we need is something crucial, right? We have this theorem, the division algorithm. Right? We have this theorem that said if we had an A and a B, we could divide A by B and get a remainder R. But there was this part of the theorem that was actually really important for all of the theorems that we used with us, which is that the remainder R was in some sense smaller than B. Now, smaller in the case of natural numbers meant smaller, right? In the sense of polynomials, it meant the degree was less than the degree of B. So but there's a notion of size of our elements of our rings that allowed us to compare the size of two things. So we don't have that when we just look at the axioms of a ring. But what we could try to do is add that notion in and then ask that this theorem, this division algorithm holds. And that's exactly the notion behind what's called a Euclidean domain. So let's just formalize that. We want a size function, our ring.
Martin calls it sigma, and we'll take all elements of R, maybe not zero, depending on who you talk to natural numbers. Maybe you can send 0 to like negative infinity or something. We have like some artificial thing. There's all these exceptions for 0. Don't, you want, we'll put it into the language so that we won't have to worry about it. But then we have a definition. We have the size function. Let's make a definition. So ring R, I'll say ring R. It's in domain. If it's an integral domain, unitive, no zero divisors, we have a size function. It satisfies this division algorithm, so sigma, such that, and we'll write it out in this general case, for any A and B in our ring, we will assume that B non-zero, A non-zero, not equal to 0. There exists a Q in R, also in our ring, such that this is the condition. A equals B times Q plus R, by A by B, with the remainder R, and the size of R is strictly smaller than the size of B. I'm not writing it exactly the way. What's the same? Okay. Now, okay, so what I want to say is this notion does indeed give us everything. Not only does it give us everything we want, it gives us everything we want without almost any more work than we already had put in. The sense that the theorems that you prove for 12.1, all of these theorems, they really hinged on this, on having this division algorithm. In particular, this first one, right? This first one did. The proof that any ideal, I mean, the basic idea being that you take the smallest guy in your ideal, but there needs to be a notion of the smallest element of your ideal. But now you have a size function. You can say, okay, take something with that size and use the division algorithm to say that there can't be anything smaller, and that everything is divisible by this guy. It's the same basic. Similarly, these things are also the same. So what I want to say is we do get, and we'll flesh that out a little bit more, we do get everything we want if we have a utility domain. And so a natural question to ask, I think, is the content of this next proposition, which is that what are other examples of utility domains? We have any. It's not a great idea to put a new abstract concept in if you don't have any examples. Okay, so the rings, I'm just going to write, I'll summarize this. The rings of integers, polynomials with coefficients in a field, and the last one that they list, and this is not an exhaustive list at all, the Gaussian integers are Euclidean. And what are the size functions? What are the size functions? Okay, well, the integers you take absolute value. Absolute value. For polynomials, we have the degree. And for Gaussians, we also have the norm. Now, what is the norm? Norm of A plus BI. What's it? Square root of A squared plus B squared. So the only thing maybe to prove with this proposition, I mean, I think these cases we've done is to look at this case. And let's do that. It does apply some of the things we've learned. So we have this size function. So here, for some integers. So it's here the size function. And so let's use A and B here. Let me call it. I think Arden actually does alpha. Let's let beta. Alpha and beta, you know. We want to show that there's a Q and an R. So we want to show Q and R. Just that. Alpha equals Q times beta. That's R with size of R. I'm just using beta because I don't want the A and the B to be confused for the alpha and beta. Yes. So what we do, well, let's be ring theorists for a second. Let's look at ideals. Consider principal ideal generated by beta. This is a subset of CI. CI is a subset of R2. Subset of the plane. Right. It is kind of, well, lazy here. Oh. Good plan. Here's CI. Measure it right on there. I guess we need a 0. Now, if we chose an element, beta, say this is beta. So in my case here, I guess I'm getting what, 3 plus I, 0. And what happens when I look at the ideal generated by beta? Well, I can multiply it by any integer. If I do that, well, I get a line through this, right? I'll get these discrete points. Right? If I multiply it by integers, I just get integer multiple. I can also multiply it by I. What does multiplying by I do in the plane, the complex plane? You guys know? Yeah. Rotate. It rotates by 90 degrees counterclockwise. It's amazing. Still haven't told my son about this. He talked about the I the other day, and I'm like, you and I, we should talk about I. Conversation about complex multiplication. If you multiply it by I, right, you'll get other points, right? You get this rotated by 90 degrees. This point here. And so on. And so when you add these, you're going to get this kind of square lattice, rotated. Get these kinds of squares. You notice I use this word, lattice. You do get a lattice. Square lattice. Generated by beta and I times beta. This is equal as an abelian group. Z times beta plus the I. Now there's this theorem we had about square lattices when we were considering isometries of the plane. It said that if we have a discrete subgroup of the plane, this is square lattice, a discrete subgroup of the plane, and we had any other element in the plane, we could translate it by some element in that discrete lattice and get inside of this kind of region here. Like one of these. In general, it's a parallelogram, but here it's a square. That's a key point. So what I'm saying is, since for alpha, the I, there is an element of my lattice, gamma, lattice, which is beta, so that alpha minus gamma is in this square. But now you can take, if you look at the circles, look at the circles. Let's look at one. We center this here, and we make it the radius equal to the radius of alpha. You can see that if I did that around any one of these points, or all of them, let's say. So if I take this circle, but now I centered it at each of these points, it will cover this whole square. In other words, okay, I take this and I center it here. I center it here. Right. You can see if I'm centering them, I've got one more. This covers these regions, they cover everything in here. Anything in there has to be in one of those circles. So in other words, so alpha minus gamma is Now that circle maybe minus tilde as norm less than alpha. Sorry, less than beta. Beta, okay, what does that mean? Beta is the radius of that circle. It's the length here. Norm of beta is the length there, right? This is the distance formula. This alpha squared plus beta squared, or plus b squared, that's the length from 0 to beta. So it's the radius of this circle. And now what I'm saying is the distance from this point to at least one of these 4 points is less than beta. I don't know which one, but it's one of them. But now let's take a look. Gamma, this is equal to alpha minus gamma plus gamma tilde. And this is in each of those lattice points. These are each in the lattice. And the lattice is beta, which is all multiples of beta. Let's call this R. And then gamma, because it's in this lattice, gamma plus gamma tilde has to equal q times beta, some multiple of beta. And then you have this equation, alpha equals q times beta. There are. We use this things we learned about lattices and isometries to show that we've got Euclidean domain. Which means, as I said, we get everything we want with this ring. This ring, all of the things that we want, and there's some interesting things that happen. Don't happen in our. All right, so now I'm going to just say something about what we'll talk about soon, what I started with, and then we'll finish up. So let's say we looked at another ring. This is a ring where we are joining a solution to the equation x squared plus 5 equals 2. I'm going to solve that equation in the integers. We can't, so we join an element that does solve it, and we enlarge our ring, the usual thing we do. The quadratic extensions, just like CI. Maybe your life is good. Over here, 6 is strange. 6 is still 2 plus 3, or 2 times 3. Also, 1 plus I times the square root of 5. 1 minus I. And what this says is that now each of these guys, what I do want to say is each of these guys are irreducible. 2 and 3, they're irreducible. I can't further factor 2 in this ring. I can't. As factors as I get. Same with these. These are as factored as they get. I can't find smaller factors. They're irreducible elements. I want to say they're prime elements, but if I say they're prime elements, and all of a sudden I see a number in this ring that does not obey the fundamental theorem of arithmetic. Namely, I've got 2 different ways of dividing this number. Completely different ways of writing factorization to this number into irreducibles. And so this is actually a ring where we start seeing the difference between irreducibles and primes. And we'll start looking at this, what we can say about this kind of ring and how to exclude it a little more next time.
2 and 3 irreducible.
2 and 3 individually are irreducible. I can't,
So all four of those numbers.
all 4 of them are irreducible, but none of them are prime in the new sense.